Hello and welcome to this tutorial on creating a simple neural network from scratch using exclusively Numpy and no PyTorch for anything outside of the dataset. So what I assume you already know before going into this, the theory behind neural networks as well as how to use basic Python, right? And so what we're building today is a simple one-layer neural network to classify MNIST images entirely in Numpy, right? We're not touching PyTorch or any of that. Right, and so this is what our neural network will look like. Obviously not the exact scale. It's going to go through, it's going to have sigmoid functions go at the end. So first we have to talk about how exactly the neural networks are actually described in code, right? And the answer, of course, is matrix multiplies or multiplications, right? Or mapbles. And so you can actually, effectively what you have is you have your input to a linear layer, and then you do a matrix multiply with it and a matrix, and you get an output. Right? So the input will go, it will multiply each of the elements of the input with each of the elements in the top of the matrix and then add them all together and you get the output. And then again for the second row of the matrix and you get the second element in the output and so on. Right? And so because of that, you can kind of think of this as the matrix being an operation applied to the input. Right? So if we go back here, like you're multiplying these two numbers together, but like you can kind of think of it as an operation you apply to the input to get to the output, right? And so it will scale it and do all of that. Now, of course, this isn't the whole story. The whole story will also include a bias layer, right? So you'll take your input, you multiply it with the matrix, you get like an intermediary, then you add the bias and you get your output. And what the neural network actually trains is each of the individual numbers in the matrix, in like the actual like multiplication matrix, and also the bias like vector, right? So those are the knobs that the neural network can tune, and then you get your output, right? So now this is just one layer. In our actual model, we're going to actually have two of these layers, right? We're going to have one that takes the input to the hidden layer, and then one that takes the hidden layer to the output, right? But then there's also a little bit of now you need the activation function in the middle to bring the non-linearity into the neural network, right? Because you need a non-linearity in order to actually make the neural network not be collapsible into a single linear function, right? And so to get the non-linearity, we're going to apply sigmoid to our output, or like in this case, the hidden layer. And so what that is you're just applying a single one variable in, one variable out function to the each individual value in the like output of a layer, right? And then from there, there's your neural network, right? And then you can scale this up or down to your heart's content. And so now, let's get to actually building this in code. So now I'm here in my code environment, and so now, first I'm going to set up the actual libraries and whatnot, and then from there, what we're going to do is we're actually going to start the pre-processing step. That will take the MNIST data set and convert it into pickle files so that we can like pull it into the model for training. Now, in order to explain the pre-process step, let me show you this diagram. So what we're going to do is we're going to take the image, right? So the MNIST is a handwritten like digit, right? Digit 7, and it's going to have a label. And we're going to take these images and labels, and we're going to convert it into a 1D representation, right? It's just going to be a 1D NumPy array where each pixel is one number here, because these are black and white. We don't have to deal with 3 color channels. And the label is going to be one hot encoded. So we have, effectively, the output is going to be like 10 neurons, and we pick the best one. And so that's what we're going to build here, but first we have to do the pre-process, take it from the actual image to these one-dimensional representations. So now let's begin. First, I'm going to set up a virtual environment. I'm going to call this neural network NumPy, because we're going to be using exclusively NumPy, right? And so then we're going to do, we're going to actually activate it, right? NumPy bin activate. And then we're going to install the libraries, right? So we're obviously going to install NumPy. That's the kind of king library here. But we're also going to install PyTorch and Torch Vision, because that's where the data sets are, right? So we're using MNIST, we're just going to download it from PyTorch. Could we download it from the internet and do some other stuff? Yeah, but PyTorch is going to make it a whole lot easier. And the main point of this tutorial is not how can we wrangle data sets, it's how can we actually build a neural network. So it's going to go. It's installing PyTorch, and so yeah, so effectively all we're going to do is we're going to load the images from the PyTorch, right? and then we're just going to reshape it into stuff we want, and then we're just going to save it to a pickle file, right? We're not going to do anything fancy, right? And so as it's going to install, it's going to bring it into the folder and do all that, and it's going to do it pretty nicely, and there we go. Now we're going to start the preprocess file. So first with this preprocess file, what we're going to do is we're just going to import libraries, right? We're going to import PyTorch, we're going to import Numpy, right? Because we're just dumping this in. We're going to import Torch Vision, right? And from, I guess we're not going to Torch Vision. We're going from Torch Vision, we're going to import data sets as well as transforms, right? Because we need to take in the MNIST data set and do that type of stuff. And we're also going to import Pickle, right? And Pickle is a member of the Python standard library, so you can just like import it, and it's just a place you can do. And so I'm just going to make a function. We'll call it load and preprocess MNIST. Right, it's just going to be a function, right? And then we're just going to say the transforms we're going to call it transform is transforms.compose, and we're just going to compose these together, right? And so the transforms we're going to do, I'm going to put this on the line. Right, so the transforms we're going to do, it's going to convert it to a tensor, right? Dot do tensor. And what else we're going to do is we're just going to normalize it, right? And so this number is going to be taken from like the stuff from MNIST, and so we're going to be setting it as 0.1307 as well, and the standard deviation we're going to be setting up as 0.3081. And so this is just going to make it really nice for the model to like do stuff, right? Then we're actually going to load the data set. So the train data set is going to be datasets.mnist, and so the root, I'm just going to set it to /data. Here we want the train set, so train equals true. Then we also want to download it, so download equals true. Then we're just going to set the transform to be transform. And from here, we're just going to copy paste this down, and test data set is just going to, instead of having train be true here, we're just going to set it to false. And then now we can actually do some processing, right? So train images, right? The images that are actually used for training is, I'm just going to say it's train dataset dot data, right? So the input data dot float, right? We're converting it to a float, and then we're just going to divide by 255, right? We want to do it as a float division, right? And so this is just, so we're normalizing it between 0 and 1 instead of 0 and 255. Next, what we're going to do is we're just going to reshape it as well, right? So now it's still 2D array. We're just going to do a train images dot reshape. I'm going to reshape it to be, so -1 just means keep whatever size is there, 28 by 28, right? So because each one of these is 28 by 28, that we're just going to multiply them together, and that's going to be the dimension we have, and we're just going to convert this to a Numpy array, right? And then the train labels, what that is we're going to do a one-hot encoding, right? So if you remember from the actual diagram, we want the position corresponding to 7 to be true, so we're just going to do one-hot encoding. So torch.neural network dot functional dot one-hot, and the tensor we're going to use is train dataset dot targets, right? So you have your data, you have your targets, and the number of classes is 10, right? We have 10 classes here, and we're going to again convert this to Numpy. Now what we're going to do is we're just going to copy this code, and we're just going to paste it in, and it's going to be a test code, right? So test images is equal to test dataset, and we're just applying the same operations, because we don't actually change the operations we're applying, right? Because if we change the operations we're applying, that would mean different training and test sets, and that's not really good, right? And so we're just going to have a train and a test, And then from here, we're just going to return these all out of the function, right? Like return the train images, train labels, test images, test labels, and we're just going to return all of those, right? Then from here, we're going to do some other stuff. I'm going to make a def save to pickle file, right? Is this super necessary? No, probably not. You could probably just have this run, but it makes it look nicer, so I'm just going to have it as a new function. So with open file name, and because pickle is a binary format, we want to write in binary form as f. We're going to just do a pickle.dump, and then it's going to be, we'll be dumping data into f, right? Now we're going to have to load and process it, right? So the train images, comma, train labels, comma, test images, comma, test labels equals load and preprocess mnist. Then we're just going to save all of these to a pickle file, right? So the first is the train images and the file name. I'm just going to set this as train images.pkl, right, pickle. And then we're going to do the same for the train labels. Right. And again, we're just going to bring it over for the test, right? So test images, test labels. And there we have it. This is effectively all we need to actually pre-process the data. So if I exit this, clear it up, and then run the pre-process file, it's going to go. Train image is not defined. Oh, I put a minus instead of an equal here. Right. But we're just going to run it. Forgot capitalization. Should have probably done that. And now it's going to go, it's going to download the data, and it's just going to go, and here is our files. And now what we're going to do is we're going to go and actually create a training file which also contains our neural network. Okay, so now to create the training file, we're just going to start. We're going to open a new Python file, right? I'm going to import libraries. We're going to import numpy as np, and we're going to import pickle, right? Because we need to load our data sets when we actually do the training. So now first, I'm going to split this up in classes, right? First, I'm going to have like a linear layer class and a sigmoid class, and then I'm just going to compose it all together into my neural network, right? So class linear, right? So def under init, right? We need to initialize it. We're going to start self, and it's going to take in an input size and an output size, right? So it's just going to take in the input and the output. So to initialize, I'm going to set the weight. The weights I'm just going to set to be random. So np dot random dot random, right? And so it's going, again, this is going to take in the input size and the output size when it's used as like a transformation. And of course, I'm going to do a little bit more to this. What I'm going to do here is I'm going to divide this by np dot square root of the input size. And so this way, this just makes it so if we make an absolutely massive, like a layer with a massive input size, that will be fine. It'll just, it'll just like go through and it'll like scale it down based on the number of inputs, so that when you like do the sum all together as you do in like a neuron in the neural network, what it will do is it will take everything and it will just sum it all together. It'll be great, right? And so it won't be scaled too big. And I'm also going to make a bias, right? So the bias is just we're just going to set up as starting out at zeros, and the shape is going to be tuple. It's going to be 1, comma, and then it's going to have the output size, right? So if you go back, you remember it's you apply the weight, you do the multiplication, and you just add the bias, and so the size has to be the output size. Now I'm going to copy some PyTorch naming schemes here. I'm going to create a forward and a backwards class, right? So I'm going to start with the forward, right? Right, and so this is when you actually like run the layer forward, right? So what I'm going to do here, I'm going to keep self.output I'm going to create a new thing called self.input. I'm going to set that to be the input so that when we do backpropagation, we'll be fine. And that's going to be, I'm going to do that a little bit later. And we're just going to return np dot, right? We're multiplying these two things together. We're multiplying the input with the weight, self.weights. Right, so this is, again, just like we're multiplying them together. We're doing the dot product here. And then we're going to add self.bias, right? So we're effectively just multiplying, again, we're multiplying it together and we're just adding the bias, right? It's pretty simple there. Now we actually have to do the backward, right? So this self, and then obviously we're going to take in the output gradient as well as the learning rate. So output gradient is basically you have the output you have, right? Like the output the neural network gave, as well as the correct output, right? And so the output gradient is effectively the difference between the two. So what you basically have there is you, not exactly the difference between the two, but like it's basically a gradient. So if you imagine the multi-dimensional space and you're trying to get the minimum loss, right? Gradient is the direction pointing to minimum loss, right? And so the output gradient is the gradient between the output and the correct answer. And so it's the, if you want to get to minimum loss, you have to change the gradient such that the output matches this type of gradient, right? And so to do that, first we're going to calculate an input gradient, right? And so this is the gradient that's going to be fed back to the previous layers to try to get them to optimize further, right? And so that's just going to be the dot product, right, between the output gradient, right, and the transpose, so np dot transpose of the weights. Right? And so we're transposing these because the weights convert the input size to the output size. But what we're doing here is we have to convert the output size to the input size. And so we have to transpose it, so now it effectively works backwards, right? It converts the output size to the input size. And so now we have here is we've calculated what the previous layer is to be. So we've effectively taken the output size and we've brought it back one layer to like, hey, if you want to optimize, bring it back to the input size. Next, what we have to do is we're going to calculate the weights gradient. And so this is the actual changes that each individual weight has to do, right? So you can think of this, how much we have to turn each dial for each individual weight. And so this is going to be numpy dot. It's another dot product, right? Neural networks, we love dot products because those run really fast on like CPUs, well, not CPUs, GPUs, and you can parallelize them, right? And so it's going to be another, we're going to transpose. So what we're going to transpose here is we're going to transpose the input fed to it, right? And we're going to do the dot product, and we're going to multiply this with the output gradient, right? So what this is basically just us figuring out how much we actually have to change the weights to get to the like gradient, like the correct answer, right? So this is just us calculating that. Then we're going to have a bias gradient. And this is just going to be the sum of differences, right? Because there's no multiplication here, this is just adding. So we're just going to take the output gradient, and then that's basically how much we have to change, and then we're just going to use that. That's just the sum. We'll set the axis to be 0, right? Because we're operating on the first axis. And we're going to keep the dimensions, right? Because normally this thing will just sum it up into one number, but we don't want to do that. We just, yeah. Now to actually edit the weights, we're going to do self.weights. We're going to set that equal to self.weights minus the learning rate times the weight gradient, right? So the reason it's minus here instead of plus is because the gradient will always point upwards, right? So the gradient will point to how can we increase the loss function the fastest. We don't want to do that. We want to decrease the loss function the fastest. And coming from calculus, right, multivariable calculus, we know that if we want to decrease the loss function the fastest, but we know how to increase the loss function the fastest, we just have to go in the opposite direction, right? And so we, do subtraction. Now we do the same thing with the bias, self.bias equals self.bias minus learning rate times bias gradient. And we're going to return the input gradient so that this can then be fed backwards across the model, right? So our last linear layer is going to calculate these, it's going to calculate the input gradient, it's going to feed that to the layer before it. In this case, it would be a sigmoid, right? And so the sigmoid is going to be like, because of this, I have to like scale it so that because I'm going through the sigmoid, then it's going to go back another layer. And then it's going to go through the first linear layer, and then you have your input. Right? And so this is all you need for a linear layer in a neural network, right? You have a way for stuff to go forward, and then you have a way to like back calculate it to like optimize it. Now I'm going to create the sigmoid class, right? So again, I'm going to start with we don't actually need an init function for this, right? Because all it is just a function going forward and backwards. We're not storing any data, so I'm not going to create an init. I'm just going to start with the forward, right? Because the init is going to do nothing. Self and input, right? And so self dot output, right? So we're going to store this, and that's just going to be 1 over 1 plus numpy dot exponential of minus input, right? And this is literally all the sigmoid is. It's a very simple function, which is why it was used very frequently, and its derivative is very easy to calculate, right? And so then we're just gonna return self dot output. Now, what does back propagation actually look like through the sigmoid function, right? So we're gonna make a backward self comma, and we're taking the output gradient, right? So the output of this. And so what back propagation looks like is effectively you take the amount that it has to, the like output of the neural network has to change, and you're effectively scaling it by the derivative of the sigmoid, right? So you find out how fast the sigmoid is changing. So if we assume we'd have to change the input less if the sigmoid is changing faster, but if it's changing slower, we have to change it more, right? And so we're basically at that point we're just taking like 1 over the slope. So the derivative, right? So and the derivative, again, this is known, is going. So we're going to multiply the output gradient by the derivative. Well, 1 over self dot. It's just the output. So x, right? 1 over x. Well, y times 1 minus self dot output, right? It's a very simple like inverse derivative, right? Like 1 over the derivative. And so it's like very widely used. And now we can actually build the neural network, right? So what we're going to do, we're going to make a class neural network, and we're going to like load this thing up with functions, right? So starting with the init function, it's going to take in self, and it's also going to take in the input size, right? The hidden size, we're like hard coding it here at a later point in time. What you can do is you can just take this and you can like expand it in your own way and do all of that type of stuff. The hidden size is going to take in the output size, and that's it. It's going to take in the other 3 sizes. It's going to build a neural network. So first, I'm just going to set self.activation function, right? And so the activation function here, again, it's sigmoid, right? Now I'm going to set up the 2 layers. So I'm going to say linear 1. That's going to be a linear layer that goes from the input size to the hidden size, right? So we're scaling the size. And then self dot linear 2, that's another linear layer, and that's going to go from hidden size to the output size, right? So we're effectively taking the input, we're scaling it, and then we're applying the activation function, and we're just scaling it again to the output size. And in each of these scales, we're doing a bunch of calculations, right? So we're doing them simultaneously. Next, when we actually go forward, and we're going to take in self, and so we're going to take in x. I'm going to use capital X here. So I'm going to set variable output is equal to self dot linear 1 dot forward capital X. And so remember, whenever you're in PyTorch, whenever you call just like in this case it would be self dot linear 1 of x, it's effectively just calling the forward function, right? And so we're doing this here because we're explicitly calling it, which PyTorch implicitly knows, right? Then we're going to go through the activation function, right? Self dot activation function of output, right? Which is basically just going to go forward. Next, what we're going to do here is we're going to go through the second linear layer, and then we're just going to return the output, right? And that's just the neural network. Right, so that's it for forward. Now what we have next is the backwards. Right, and so this, you're effectively just taking the gradient and just pulling it backwards, right? So you're going to take in self, you're going to take in x, you're going to take in y, you're going to take in the output, right, the output of the neural network, and you're going to take in the learning rate. I'm going to call it, instead of output, I'm going to call it y predicted, right, because that is what it is. And so here, the output gradient, what that is just going to be is output minus, well, the output gradient is going to be y pred minus y. So this is effectively just what is the difference between our predicted and the actual, and then from there you have your gradient, and so we can just go through all the layers, right? So output gradient is equal to self dot linear 2, and we're going backwards, right? It's back propagation. We're going backwards. Again, the output gradient's here, and the learning rate is just going to be the same. And so we can do the same for linear 1, and then in between we have to go through the like inverse sigmoid. So self dot activation function, and since we're going backwards, dot backward, and we're taking the output gradient and we're effectively scaling it. And there's a backward, right? And then because we have the training, the actual changing of weights within each layer, there we go. Now I'm going to create a test function, because I'm going to use the test function and train function to actually just print out how well the model's doing, right? So I'm going to start by so I'm going to start with the test function. Test self, comma x, comma y. Right, so you have your correct input, correct output, and correct, comma total equals 0, comma 0. Right, so we're saying the correct and the total. Next, for I in, right, we're just going to loop through all of these inputs. Right, the y predicted is np.argmax, right? So we're just taking the most likely outcome the model says, because we have 10 numbers, right? So if it says all the numbers are like 9%, and then one of the numbers is at 19%, it's going to be like, we'll take the 19%. Even though it's only 19% sure, we're going to be like, we'll just take that, because that's your most likely outcome, right? Self.argmax, and we're going to go we're just going to go self.forward of x, and it was going to be x of I, right, because it has to be like a kind of multidimensional array, because we have the batch size, so we're just going to take an array of just one element, which is I here, but we're going to be doing it in a fancy way so that it's a little bit more aligned with our training strategy, which we will get to, right? Next, y actual is it's np dot. We're going to go through another argmax here, but we're just going to take in y of I. And like we know that this is going to be like fine, but like it never hurts to like double check. Now we're going to do check. We're just going to say correct plus equals int. It'll automatically convert to an int, but we'll leave it that way. Y pred equals y actual, right? So we're just gonna if they're the same, we're going to add it to correct. If they're wrong, we're gonna add 0, which does nothing, right? Next, we're gonna say total plus equals 1. We're adding 1 to the total, and we're just gonna return correct over total, and we're doing float division, right? And so there we go, right? That's our code for actually running the test. Next, I'm gonna have a train function, right? So it's going to take in x train, y train, and I'm also going to take in test code, because in this train function I'm going to like run tests, right? So x test, come on, y test, right? We're just going to take in the number of epochs we want to train for. It's going to take in predicted, like our wanted learning rate, and it's going to take in wanted batch size, right? So it's going to take in all of these, and then from here, what we're going to do is for every epoch in the epochs we have to do, what we're going to do is we're going to run a train. So for I in range 0, right? We're basically just going to iterate through our test set, right? But we're going to do it in batches of batch size, right? So we're going to go through. If our batch size is a 32, we're going to iterate up 32 at a time. And so I is going to start at 0, then it's going to go 32, 64, etc. So then we're going to get the actual batch. So we're going to say x batch is equal to x train of I colon I plus batch size, right? And so we effectively have to do it this. That's the reason we had to have our prediction here be kind of strange. We're effectively doing a batch size of 1 there. Now we're going to do y batch. So y batch equals y train. There we go. Next, we're actually going to do our calculation. So output equals self dot forward of x batch, and then we're going to do backwards. So self dot backward. X is going to be x batch. Y is going to be y batch. The prediction is going to be our output, and learning rate is going to be a learning rate, right? Now we're going to run our tests every epoch. So for well, we don't need a for loop. I'm going to run a training accuracy and a testing accuracy. So our training accuracy is going to be self.test. We're going to be using our test function, but on a training set, and it's going to take in x train. Now, if you wanted to, you could say :1000 if you want it to be fast. I don't particularly care about performance here because it's going to be a small model, very small model actually, and it's going to take in a y train, and that's going to give us training accuracy. Next, testing accuracy is going to be self.test, and it's going to take in x test and y test, and that's going to be a training and testing accuracy. And we're just going to print these out, right? So we're going to just make an F string, right? So we're going to say epoch and then epoch plus 1, right? Because it's going to start with 0, so 0th epoch, so we're going to say 1. And so our train accuracy is going to be train act, and we obviously want to format it, so we're going to say it's going to 4 decimal places. And then our test accuracy is going to be our, again, it's going to be a test accuracy, and we want to format it to 4 decimal places, so there we go. And then that's our training function, and that's our entire model. Now we actually have to set up all of our code, right? And so what we're going to do is we're going to load from pickle file name, right? And so with open file name comma read binary, because we're reading it in binary as f. Right? I'm just making a function just like the write to pickle. I'm just making a function so it's easier to work with. Data equals pickle dot load, and we're loading an f, and we're going to be returning data, right? Next, what we're going to do is we're just going to have a main loop, right? So x train equals, and so what we're going to do is we're going to do load from pickle, and the file name is going to be train images.pickle, and ytrain is going to be train labels.pickle, and then we're just going to do the same for our train and our test, right? Test images, test labels, right? So we have our train and test, and so then we're going to build a neural network. So we're going to have a neural network. Input size is going to be 28 times 28. Hidden size, I don't know. I'm just going to make it kind of big. I'm going to say it's going to be like 100. Why not? And output size is going to be 10, right? So we're just going to be scaling it down as we go through. Next, we're going to run the training file. So neural network dot, well, not training file. We're just going to run the training function. So x train, y train, x test, y test. Epochs, I don't know. I'll say let's do 25 epochs. The learning rate, I'm going to set that to be 0.01, or you can write 1e minus 2 because Python. And then from here, I'm going to set the batch size. I'll set it to like 32. And from here, we can just run train.py. Int is not iterable. Oh, I forgot the for epoch in ranged epochs. Right. Sigma is not callable because I forgot. Remember, this is in PyTorch. I got used to PyTorch. We had to do dot forward. Right. And now we're actually going to go, and it's actually going to go to train. Right. Epoch 1, again, this is roughly expected. we want to see roughly like 10% accuracy, right? Because that means everything's going just fine. And so we're doing 25 epochs. And so as you can see, the accuracy is increasing. We're going up. This is at like 33%. We're at like 40% over here at epoch 7. And so, yeah. And so now it's training. And so the accuracy is just going up. And you have a neural network here, right? And so then what you can do here is you can just take all the weights, save it to a pickle file, and then like use it elsewhere. And so we can see the accuracy is going up. It's probably going to hit like a hard limit somewhere. Looking here, the hard limit is going to be at like 40% roughly, because it's not a really big model. It's one hidden layer, but it's also a very small number of computation, right? Oh, it's going up. It's at like 50% now. It's probably unlocked something new. But like, yeah, we're not going to see like high 90 accuracy here, because it's a very small model. And so now it's just going to, it trained 25. Oh, it hit like 58% accuracy. That's pretty good, right? And so, like, we're not going to see a very high level of accuracy. Maybe if we kept training and like it did a bunch of more stuff, maybe, but like I doubt it. And so now what we have is you have a 60% accurate number predictor, and it's written entirely in PyTorch, right? Not PyTorch. Numpy, there's no PyTorch. It's written entirely in Numpy. There's no PyTorch here. There's none of that. And so what you have now is you just have a simple neural network. And so now, theoretically, you understand more about how they work and how to implement them in code. If you're doing an actual neural network, you'll probably want to use PyTorch, but here, now you know how neural networks work. Thank you for watching this video. Like and subscribe if you want more from me, and I will see you in the next one.